Okay, so in this lesson that we're still in, where we're solving variables on both sides, and we're on the back side of the notes instead of the front side, we have a word problem for which we're going to set up an algebraic equation. Not saying the only way to solve this problem is by using an algebraic equation, but we do need to learn how, because that's one of the standards that you have to meet, is can you represent a situation of application problem, a word problem, with an algebraic equation. And then we already know how to solve them. So the real test here is, will we be able to set up an appropriate algebraic equation to help us solve this? So we have Marlo, who wants to rent a bike, and he has two different options, doesn't he? He can rent from Green Lake Park. They have their own entrance fee, and they charge $2 per hour. Or he could rent from Oak Park, which has an entrance fee also, and an hourly fee. He wants to know when the cost will be equal, okay? So in reality, we need an equation that shows when is, what's it called again, Green Lake Park. Let's fill this in. When is Green Lake Park, and we're going to put apostrophe S after park, when is Green Lake Park's cost the same as, that's an equal sign, Oak Park? Apostrophe S, cost. When does Green Lake Park's cost equal Oak Park's cost? That's what he wants to know. He said, when will their costs be the same? Okay. Well, we have to figure out what is it that can change in this situation. What's the unknown that can really change? What do you think X would represent in our algebraic equation? Pardon, Josh? How long? Okay, so how many hours, right? Because they charge by the hour, so let's let X be the number of hours. He can pick and choose how long does he want to rent that bike for. So the X is going to represent the number of hours. So remember, we always, in step 1 of our word problem, we pick a variable and describe it. And then in step 2, we set up the equation. Okay, well, we want, how could we represent Green Lake Park's cost? Because that's one side of the equation. What does Green Lake Park charge if you're going to do bike rental there? What expression do you think we could represent that with? Rose?
It would be 2x.
2x?
Yeah.
Okay, because why? Why is it 2x?
Because Green Lake charges 2 hours per hour.
They charge $2 per hour, so we would take 2 times x, okay? So we could say 2x for the, how much you're going to have to pay according to how many hours. Do they charge anything else?
Plus 8.
Yeah, plus that 8, which is a one-time fee. It's the entrance fee. So they charge an entrance fee, kind of like, here, come on in, you can use our park for $8. But then if you want to rent a bike also, you have to pay $2 every hour. Okay, there's our Green Lake Park's cost. Now, there's our equal sign. How can we represent Oak Park's cost? Cameron?
5x plus 2.
Okay, they charge $5 per hour and a $2 entrance fee. So we would have the expression 5x plus 2. Now, this equation is pretty ready for us, isn't it? Does it need any simplifying? Is there any distributive property we need to do, any multiplying? Any combining of like terms?
Yes.
Not really. There's x's and a constant on each side, right? So we can go right to work solving this. So step 3, we're solving now. What should we make our first move? Subtract 2x from both sides. Okay, let's subtract 2x from both sides. And now what does our equation read?
A equals 8.
3x plus 2. Okay? What would be our next move now?
Subtract the 2.
Yeah, we got to get that constant off. That's over with the 3x. We'll get rid of that next. We'll subtract 2 from both sides.
6, 36 equals
So we're gonna have 6 equals
Yes.
3x. Emerson, question?
Yeah, for step 3, does it matter what one we subtract from?
No, it does not matter which first move you make. No. So if you wanted to subtract the 5x first instead, you mean? You could do that. We should all still get the same answer in the end. Okay, what's our next move here?
Divide by 3.
Divide by 3. So 6 is going to get divided by 3. 3x is going to get divided by 3. So x is equal to 2. X equals 2. Okay, so now we're ready to write our sentence answer. What was the question again?
The number of hours.
He wants to know when the cost will be the same. So we can say what? When he rents the bike for 2 hours. When Marlo rents the bike for 2 hours, the cost is the same. Marlo rents the bike for 2 hours, the cost is the same. You're, at some point in your testing, not by me, but by, standardized testing, at some point, they're gonna be grading you on being able to do this part also, being able to write a good sentence answer to the question that was being asked. So it's important that we do this part also. Not only do we find that x equals 2, but that when he rents the bike for 2 hours, the cost is the same. So if he only wants to go bike riding for 2 hours, does it matter which park he goes to?
No.
No, it doesn't matter at all. Okay, but what would that cost be?
$12.
Let's make it so we don't have to work very hard here. So how are we going to get $12, Payne?
Take 2 times 5 and then add 2.
Okay, so we're going to use the expression 5x plus 2. We only have to use one expression or the other. It does not matter which one we use because remember, this is when the costs are the same. So this is Oak Park, 5x plus 2, or Green Lake Park was 2x plus 8. We're putting in that number of hours for when it's the same, so it doesn't matter which park we calculate it for. Because remember, we just decided at 2 hours, it doesn't matter which park he does the bike rental from. So one or the other. You don't have to do them both. You just have to do one of them. And we should end up with, no matter which one we use, the same answer, which is 12. Okay? So let's write our sentence answer now. What will we say?
It costs me $12
Okay, when it's what?
rent for 2 hours.
When it's rented for 2 hours, okay. So for 2 hours, the cost is $12. So let me stress to you, this wasn't the only way to solve this problem. But we are going to be expected to be able to solve some of the problems by being able to set up an algebraic equation, following the process of solving it, and then being able to answer the question in our own words. Malcolm?
You said algebraic.
Yeah, I said algebraic.
I thought it was algebra.
We are in algebra, that's the name of the subject, but when we change it into an adjective, which is what I do when I put it in front of the equation, then I have to call it algebraic equation. So a little English grammar going on here too. Okay. Any questions or concerns about being able to do an application problem? Because one of the problems you do in your homework is that. I think in fact it's number 33. Any questions or concerns? Okay, let's go to the front and let's practice something else that can happen when we are solving algebraic equations. So far, every time we have solved these equations in this lesson, we've always gotten one solution. We find out that x is equal to some value. And that's what's happened every time. But sometimes equations have infinitely means what?
Never ending.
Never ending. Infinitely many solutions. An example of something infinite is the number line. The number line has an infinite number of numbers on it.
Or pi.
And pi goes on infinitely, forever and ever and ever. When we have equations that have infinitely many solutions, they have a special name. They're called an identity. Tell me what you think of when you hear the word identity. If I say something is identical, what do you think of?
Twins.
Twins. Something that looks what?
The
same.
The same, like who in
Cameron
here?
and Brighton.
Like Cameron and Brighton. Do you guys have a trick for being able to call it by the right name?
Their glasses.
Their
and
glasses.
You just all know them.
You
they're
just,
different.
you've known them long enough that you can tell, okay? But for me yet, it's still like you put them side by side and they're identical to me and I can't tell one from the other yet. I haven't found that, I haven't found that trick yet, so I always typically have to ask them or make the mistake of calling one of them by the wrong name. So, an identity means then we're going to look for something that looks exactly the same, aren't we? Okay, well let's start solving this equation and see what happens. First thing we're going to do is we got a whole bunch of subtraction going on, don't we? Let's change all that subtraction to add the opposite. So 6 plus a negative 2x plus a negative 1 equals 4x plus 8. Don't need to change that, but here's another subtraction, change to plus a negative 6x. And then another subtraction, change that to plus a negative 3. Looking to me like we have some simplifying to do here. Let's look at the left side of the equation. Is there any simplifying we can do? What can we do, Rose?
6 and negative 1.
6 and negative 1 can be combined. They are like terms. So 6 plus negative 1 is?
-7.
$6, you give $1 away, how much you got? 5. It's 5 plus negative 2x. Those x's don't have anything to be combined with on that side. Okay? Anything that can be simplified on the right side? We can put the 4x together with the negative 6x. So what is 4x plus a negative 6x? 2x?
Negative 2x.
Negative 2x. And then what can be put together? What else can be put together? 8 and the negative 3. So they become what? 5. Okay. Now let's write this the way algebra likes things, because you know what? I'm thinking that at this point you should be able to stop and say to yourself, what's going on here? What's happened?
Both sides are the same.
Both sides are the same. Each side has a negative 2x on it,
So they're both equal.
and both sides have a 5 on it, so,
That's your solution.
let's just have this one trade order here, because when you have addition, they can trade places, can't they? 3 plus 4 is the same as 4 plus 3. And then we say, here's the other side, we'll just leave it like it is. Both sides are the same. They are identical, aren't they? Both sides are the same. Well, what did we say up above? What do you think we're going to call it when they're both the same? An identity. So this is called an identity. Identity. Well, if it's an identity, here's what holds true. Any number can make the equation true. Any number can make the equation true. Any number from the number line. In fact, let's just try one. Somebody, and we'll just do it in a spot that's a little easier, like right here. 4. Okay, negative 2 times 4, class is? Negative 2 times 4 is?
Negative 8.
Negative 8. Negative 8 plus 5 is?
-3.
Negative 3. Well, what's going to happen on the other side?
Same difference.
Same thing, aren't we? We're going to get negative 3 equals negative 3. Pick another number.
238.
Oh, pick something that we can, we don't have to be that taxed on
10.
today. How about, okay, let's do 10. Negative 2 times 10.
Negative 20.
Negative 20. Negative 20 plus 5.
-15.
15.
Negative 15. Is that what's going to happen on the other side also?
Yep.
Yeah. So no matter what number we put in there, isn't that what should happen every time? Whatever happens on the left side should happen on the right side. So that means all real numbers. Okay, we're going to do it like this. We're going to write it as infinitely, I think that's what maybe, infinitely many solutions, just like we said up above. Some equations can have infinitely many solutions. Right.
If you tried to continue to actually try and get something out of it, wouldn't both sides come up to a 0?
Yes, that's
Because you
exactly.
cancel
That's
it.
what would happen. You'd end up with 0 equals 0. And is that a true statement?
Yes.
Yeah, so if it's a true statement, it's kind of like saying, no matter what number you put in there, like we were doing, you're always going to get some number equal to itself, aren't you?
Yes.
So that's why we can say it's infinitely many solutions, because yes, it doesn't matter.
Even if you continue it or not.
Yeah, even if you continue it or not. So the good news is though I'm going to let you quit once it gets to the point that if it ever gets to this point that it says the same thing on both sides, you get to stop and say, oh, this is an identity, which then tells me the solution is what?
Infinite.
Infinitely many solutions.
Couldn't you just put infinite solutions?
You could do that too. Infinite solutions would work. The guy always looking for the shortcut.
Well, just infinite solutions.
Infinite solutions. Okay. So this is just kind of like, a couple of adjectives for it, isn't it? Okay, well then we also have this other scenario that can happen. Some equations have no solutions. Well, let's figure out how we know when an equation doesn't have a solution. So we have our number 2 here. 8x plus 6 minus 9x equal to 2 minus x minus 15. Got some subtraction going on. So you know the first move, don't you? What is it?
Change to add the opposite.
Yeah, change it to add the opposite. And it might even be a good idea to insert a 1 there in front of that x on the right side. Okay. Can we do some simplifying before we start solving?
Yes.
Okay. On which side?
Oh.
Actually, both. What can be combined on the left side? We get some x's. Yeah. So what's that going to combine to become? Negative 1x plus 6. Okay. And we got a 2 that can be combined with a negative 15 on the other side. What's that become? Negative 13 plus negative 1x. Well, they both have a negative 1x. So is this an identity?
No.
No, they don't look exactly the same, do they? So Payne?
I think it's if you add 1x to each side and then it's going to cancel out, there's just going to be 2 normal numbers there, and that's what's going to happen, and then that's how you know.
So since they're not the same, we don't get to stop and say stop and write the word identity and say infinitely many solutions. We instead are going to keep going and say, okay, well I got to add 1x to both sides. And after I add 1x to both sides, the x's are gone over here, I just have 6. The x's are gone over here, I just have negative 13. Problem. What's the problem?
You don't have your variable.
You don't have a variable anymore, so there's, let's go in down here, I bet that's what the fill in the blank is. There are no x's left, right? The x's are gone, the variable is gone. And the resulting statement is what?
Invalid.
Invalid. It's false, isn't it? It's not true. 6 does not equal negative 13. So the resulting statement is false, or if you want to sound even, more technical like Payne, you can say invalid. So there aren't any numbers that could make this equation true. Because here's what would happen. If we tried to back up here when it was negative 1x plus 6 equals negative 13 plus negative 1x, well, if we would try to insert a number in there for x, like let's try 0. Is 0 a number?
Yep.
Okay, so what's negative 1 times 0?
0.
0. And what's 0 plus 6?
0. 6.
6. Well, then let's put a
Plus.
0 in the other side. Negative 1 times 0 is,
0.
and 0 plus negative 13 is
Negative 13.
negative 13. And so we're trying to convince ourselves again that 6 is equal to negative 13, is it? No. We're never going to get a number that we could put in there for x that we're going to end up with a number equal to itself. We're going to have something valid. We're going to have something true. So we have to say then, once it gets to this point where the variable has gone away and the resulting statement is false, there aren't any numbers that can make the equation true, so our solution is really no solution. So we have to state something. So if it ends up an identity, we state that it is infinitely many solutions. If it ends up that the variable went away, and we ended up with a statement that's false, then we have to state no solution. We're not done until we tell what the solution is, in other words, okay? Questions? Okay, then we're done.